Good morning or good afternoon. My name is Zhenyesbek. I am presenting our work on bridging word embeddings and hyperbolic spaces through the score-shifted PMI matrix. And this is the joint work with Ali Geldin, who is my research assistant. We are from Nazarbayev University in Kazakhstan. So first of all, I will give a big picture of what we did, and then the details of each step. So we depart from the work of Levi and Goldberg, who showed in 2014 that training good quality word vectors is approximately the same as taking a PMI matrix, shift it, and factorize. In our work, we show that almost equally good quality word vectors can be obtained by factorizing a squashed shifted PMI matrix. At the same time, squash-shifted PMI matrix can be treated as connection probability matrix of certain graph, because each entry of this squash-shifted PMI matrix is between 0 and 1. And then the graph that is generated from such matrix turns out to be a complex network. And finally, as Krukov showed in 2010, complex networks are dual to hyperbolic spaces. And now if we look at this chain of arguments, we see that word embeddings are connected, linked to hyperbolic spaces. And this link can be established through this object, score-shifted PMI matrix that we introduced, and the complex networks. And now we will go into details of each step. So first of all, we show the link between squashed-shifted PMI matrix and word vectors. Now, as I already mentioned, we start from the SGNS skipgram with negative sampling model that simply optimizes this objective. And as Levi and Goldberg showed, maximizing this objective is same as factorizing the so-called PMI matrix, shifted PMI matrix. And PMI here stands for pointwise mutual information matrix. Each element in this matrix is defined by this formula. Now, we consider a modified shifted PMI matrix. On top of each element is shifted, and then on top of that, we apply sigmoid transformation. And then we can show that if we consider this objective, which is very similar to the objective of skipgram with negative sampling, then maximizing this objective is same as factorizing the sigma S PMI matrix, the score-shifted PMI matrix. And the difference between this objective, this defined by equation 2, and the original SGNS objective is that we don't have sigmoid transformations here inside logarithms. That's why we call objective 2 as non-sigmoid SGNS. Now, there are other ways to factorize some matrix into product of low rank matrices. By maximizing this objective, we can do that, but there are other ways. And another way is to take the matrix and directly factorize it into product of matrices using, for example, truncated SVD. Truncated SVD assumes that we can decompose our original matrix into product of 3 matrices. One is tall, in the middle we have a square matrix, and the rightmost matrix is wide one. And then we can take half of this decomposition and treat it as word embedding matrix, and the rest as output context embedding matrix. And in this way, we will factorize our sigma SPMI into product of two matrices, W times C transpose. Now, we want to evaluate the word embeddings that arise from non-sigmoid SGNS or from sigma SPMI versus original SGNS or those that arise from PMI or shifted PMI or positive PMI as Levi and Goldberg did. So for this, we take a standard data set, text 8. We ignore words that appear less than 5 times. This gives us a vocabulary size 71,000 tokens. And we evaluate on standard word similarity and word analogy tasks. The results of evaluation are given here. We see that non-sigmoid SGNS slightly underperforms SGNS, the original SGNS, but not by a large margin. And the sigma SPMI matrix after decomposition gives us embeddings of comparable quality, of quality comparable to those that can be obtained from PMI matrix. And both non-sigmoid SGNS and sigma SPMI give us word embeddings of similar quality as predicted by our theorem. Okay, so this basically legalizes sigma SPMI and allows us to treat it as a matrix from which we can obtain good quality word embeddings. Next step, we show the connection between the sigma SPMI and complex networks. So first of all, we look at spectral densities of two sigma SPMI matrices. They were computed on two different corpora, text 8 and NVIC 9. And what we see here is that the spectral distributions are somewhat similar to spectral distributions of so-called complex networks. And this gives us a right to try to show that sigma SPMI matrices are indeed complex networks. So for this, we need first to clarify what we mean by complex networks. And to define complex networks, we will use two concepts from graph theory: average degree and clustering coefficient. Now, if we look at Erdős and Rényi model of random graphs, we know that the clustering coefficient for such model is approximately average degree divided by total number of nodes in the graph. And the degree distribution of such model, of such graph, follows the binomial distribution. In complex networks, on the other hand, the clustering coefficient is much greater than the clustering coefficient of the Erdős and Rényi model. And the degree distribution is according to power law distribution, not according to binomial distribution. And this is how we define complex networks. We say complex networks are such random graphs that have strong clustering and power law degree distribution. Now it's time to see whether our sigma SPMI graphs, so graphs which can be generated from sigma SPMI matrix by treating each element in this matrix as connection probability. Now, if we look at the clustering coefficient of such graphs, of sigma SPMI graphs, we see that they are higher, significantly higher than those of the Erdős and Rényi model. And then if we look at the degree distribution on logarithmic scales, we see almost linear patterns, which basically means that the degree distribution is according to power law. So this verifies that sigma SPMI graphs are indeed complex networks according to our definition. And then it turns out that there is a link between complex networks and hyperbolic geometry. This was established by Kryukov in 2010. Now, Kryukov considered a so-called native model of hyperbolic plane, where hyperbolic plane is represented as the interior of a disk of radius capital R. Each point has polar coordinates in this disk, and the radius coordinate corresponds to the hyperbolic distance from the point to the origin, while a distance between any pair of points, x, satisfies this so-called hyperbolic law of cosines. Krukov showed the connection between hyperbolic spaces and complex networks by doing the following. They placed randomly endpoints to the hyperbolic disk, and each pair was connected with probability sigma r minus hyperbolic distance between these points. And we, in our work, to verify that the graphs are all our graph, sigma s PMI induced graph, also has underlying hyperbolic geometry, we do the same thing for our case. We randomly place points on hyperbolic plane, and we connect each pair according to this probability. Now, when we say that we randomly place points, this means that theta, the angular coordinate, is drawn from uniform distribution on 0 to 2 pi, and the radius, polar radius, is drawn from the exponential distribution. Now here we have hyperparameters alpha and capital R, and those are chosen to fit the degree distribution of the resulting graph to that of sigma s PMI graph. So basically we construct a random hyperbolic graph that has the same degree distribution as our sigma s PMI induced graph. And then we wonder whether these two constructions possess similar structures. For this, we notice that the connection probabilities in sigma s PMI graph are given by this formula, while connection probabilities in the random hyperbolic graph are given by this formula. Now, if these two graphs indeed have the same or similar structure, then PMI values in principle should be similar in distribution to hyperbolic distances. And we want to verify this. And luckily, this is easy to verify. We simply take the distribution of PMI values in our PMI matrix, and then we can look at the distribution of hyperbolic distances, pairwise hyperbolic distances. And if we plot these two distributions, we obtain the following histograms, where the top one corresponds to PMI values and the bottom is the distribution of hyperbolic distances, pairwise hyperbolic distances. And we see that indeed these two distributions are similar in the sense that both are unimodal and skewed, right skewed. The major difference is in the shift, which can be explained by the difference in this logarithm of k in case of sigma s PMI and capital R, or this coefficient C, in case of random hyperbolic graph. All right, so basically this shows that both sigma s PMI and random hyperbolic graph, they induce similar structures, and this gives us a link between sigma s PMI as a complex network and hyperbolic geometry. To summarize, we show that word embeddings are connected to hyperbolic spaces. And the key ingredient in establishing this connection was this coarse-shifted PMI matrix that we introduced. And we are not the first who claim hyperbolicity of word embeddings. Other people successfully trained word vectors in hyperbolic spaces. However, we claim that we are the first who justify this connection, who justify that it makes sense to put word embeddings into hyperbolic space. Thank you for your attention.